Pramod Beesal. I am an IIT Delhi graduate and currently an IRSME officer. In this video, we are going to discuss about the microprocessor programming in light of 8085. Okay, so our special focus will be upon 8085 and usual types of programming that we have had a glimpse of in our previous video when we discussed about three types of programming. One was our machine code, that binary coding completely 0101. Another one was our assembly code that was based upon the mnemonics or the hexadecimal codes. Then we discussed about the high level languages, under which we had our C, C++, Java, Python, all those things. Okay. Then we have also had an idea of a compiler and interpreter to convert a high level language to the machine code. And then we had also seen an assembler to convert the assembly language into the machine code, because finally a microprocessor or a computer can only understand binary language, means the language of zeros and ones only. Okay. So when we say programming is what? Basically a set of instructions. Okay. Now instruction is what? The commands that we give to our system that it needs to execute. Okay. These are our instructions. Fine. So when we talk about the instruction set means set of instructions that can be executed, right? That can be executed by microprocessor here, because we are talking about the microprocessor, right? So the set of instructions that can be executed by our microprocessor. When we say 8085, then all the instructions that an 8085 can execute will come under the instruction set of 8085. Now ISA, there is something known as ISA, which is instruction set architecture. Okay, instruction set architecture means what is the exact architecture of our device or of our machine in order to execute all those instructions. Okay, so we are not going to get into the detail of ISA, but I have already told you that it is of two types. One is RISC, another is CISC, complex instruction set computer and reduced instruction set computer. We have both of them everywhere in microprocessor and microcontrollers, both of them. Okay, so it's not that they are exclusive to either one of them. Fine. We will see just a few important properties of them in the end, but other than that, we don't need to worry about RISC and SISC. Okay, so let's discuss about the instruction set of our 8085. Okay, so all the instructions that an 8085 can execute, what are those instructions? Okay, so there are 5 sets of instructions or 5 types of instruction that it can execute. One is called copy instruction. Okay, what do we mean by copy? Is basically related to the transfer of data. Okay, now the transfer of data could be between register to register. Okay, it could be register to memory. The data can be transferred from any location to any location that is desired. Okay, whatever we wanted to do. So now if I see, or if I want to have certain examples here, so let's say I want to add some value to our register. Okay, because then only we can carry out the operations. Okay, so let's say I want to do load 8-bit number. I am having some 8-bit number, let's say 4F. That is my 8-bit number. It is in hexadecimal. Whenever I am writing anything, that will be in hexadecimal in register B. Okay, so instead of writing all this, because anyways I cannot use that in our programming language, right? So I will simply say MVI B, 4F H. Okay, now what does that mean? MVI means move 4F hexadecimal code into our register B. So we have got this particular instruction done by writing just this. So this is our code that we use. Okay, so this is our assembly code. Assembly code for what? 8085 microprocessor. Okay, or let's say what I want to do, I want to copy some value from register B to register A. Okay, register B to register A. Then what I can say? Simply I will say MOV A to B. Okay, so it will move the value of B to A. Very simple here. Okay, only few of the instructions we are going to look at. We are not going to go into the hardcore programming because we don't have to do that for that matter. Okay, just to tell you just to give you a basic idea so that you can appreciate what we are doing over here. Okay, then let's say we want to do copy from register B to our memory. Okay, to our memory. Some memory location is there that we want to move our data to from register B. So I will simply say move M, B. Means move the content of B into M. What is M? If I say M, then that is equivalent to HL. So whatever is stored in our register H and register L, that is our memory location. Okay. So HL register, because it is making a 16-bit register, 16-bit data here. Okay. So that will be giving me the memory location. So this type of copy or the transfer instructions can be carried out with the help of a 8085 microprocessor. Now, second set of instructions that it can carry are related to arithmetic operations. Okay. So we can carry the arithmetic operations also. There is no need to say that there will be addition, there will be subtraction, there can be an increment by 1, okay, there can be decrement by 1. That sort of operations we can do over here. Okay. Now addition can be either I am giving a direct value and I want to add that. For example, add 32H to accumulator A. Now when we talk about A, I will simply write it as add 32H, okay, because A is understood over here, right? Or what I can say that add contents of register B. Okay, so add register B value to our accumulator or our A register, right? And then I can simply say add B. Okay, this is ADI I have to use over here. Okay. Similarly, if I want to do the subtraction, then in case of a subtraction, I will say SUI and whatever is the number here. For example, this and SUB if I'm using a register value. Okay. So it depends upon whether I am using an external given value or I'm using a register's value or I'm using a memory location or what exactly I am using. Okay. In order to increment or decrement, I can simply say for increment, I will be saying INR D. If I want to increase D by 1, okay, then I will simply say INRD. So D's value will get incremented by 1. So these sort of arithmetic operations can be carried out with the help of our microprocessor. The third set of instructions that it can carry are logical operations. Now, no need to talk about them. Logical operations, or what we call as bit manipulation. Okay, we are manipulating our data based upon bit manipulation. We can call it something like OR, AND, XOR, and all those operations, the logical operations can also be carried out with the help of a microprocessor. I will not give you the example here because that will unnecessarily complex it and you may not even understand it for that matter. Fourth type of operations that we can have or instructions that we can carry out are called as branch instructions. Okay, branch instructions. Now under branch instructions, we have mainly two instructions. One is called as jump. Means when we want to jump from one location to another location. Otherwise, what is happening? Our sequence is one after another. But if I want to make a sudden jump from one location to another location, that can be either conditional or unconditional. Means let's say if my parity is 1, then jump to this location. If my carry is 1, then jump to this location. That sort of branching operations we can have over here. Okay, and that can be conditional and that can be unconditional also. Second set we can have within itself is call and return. Okay, so those of you who have had a little bit exposure of programming can appreciate it better. Otherwise also you can do it if you know NC and CNC programming, any idea about that also, then also it's fine. Okay, now the last type of operations or last type of instructions are called as machine control instructions. Okay, we want to control the machine or the microprocessor itself. So there can be operations like halt. Okay, halt means stop processing now. So I have given a program, the programming is the instruction execution is complete, then I want to stop the programming, then I will say at the end halt. So unless it sees this particular command in the end, it is not going to stop. So I can have a halt. I can have do not perform any operation. Do not perform any operation. Okay, so that sort of commands also I can have, and that can be represented with the help of NOP. Okay, so if my parity is coming 1, then I stop performing any operations further. Okay, so that sort of conditions, that sort of instructions and commands can be executed with the help of a 8085 microprocessor. Okay, so that is called the instruction set of any microprocessor. Similarly, different devices will be having a different set of instructions. Okay. Now, depending upon the length of our instruction, okay, it can be again further divided. Okay. So classification of instruction based upon length. So what is the length of our instruction? That can also be used to classify the instructions. Okay. For example, what is our instruction? I am saying that add B. So what is that invariably means? That A or the accumulator value will be equal to whatever is its current value, A plus B. Okay. So A and B, they are my operands. They are called as operands. Operands means the operation is being done on A and B. What operation is being done? This is my operation. Okay. So this is called my operation. Okay. And how exactly I'm expressing this particular thing? How exactly I'm expressing? Like this. Okay. So this is my operation, which is represented with the help of a opcode. We call it as opcode, operation code. Okay. And this is my operand. Okay. Now add will be justified with some digits, some number of digits. Now this B will be justified with some number of digits or some number of bits. Okay. So depending upon the total length of this instruction, I can divide my instruction into 3 categories. Number 1 category is called as a 1-bit instruction. Not 1 bit, 1 byte instruction. Okay. There is a difference between bit and byte. 1 byte is equal to 8 bits, right? You must be knowing that. 1 byte is equal to 8 bit, and 1 register can hold 1 byte, right? Because it can hold 8 bits. So 1 byte instruction is what? 1 byte instruction means when I am giving only a single instruction to it. Okay. So let's say if I say add B. Now add B can be given with the help of single instruction itself, or with the help of 8 bits only. So that will be known as a 1 byte instruction. Okay. Or HLT. That is our 1 byte instruction. Clear? We are giving the operand and the opcode, both of them in single byte, means single 8 digits. That will be giving me 1 byte instruction. So 1 byte instructions, opcode and operand in single byte basically. Okay. They are combinedly, they are using 1 byte only. Second that we can have is a 2 byte instruction. 2 byte instruction. 2 byte instruction means there will be an opcode which will be taking let's say 1 byte, and then there will be an operand which will be taking another byte. Okay. So for example, when I say MVIA02, okay, so what I mean here, that this is my 1 byte. Okay. To say that move into A is my 1 byte, and to say what I need to move, so this data will be coming in another byte. So second byte. 1 byte is this, 1 byte is this. Total is 2 byte instruction I am having over here. That is why it is known as a 2 byte instruction. Okay. So 8 bits for this and 8 bits for this. Total 16 bits. Third, I can have a 3 byte instruction. Okay. So obviously I don't need to explain anything about it. I will be simply having the opcode. Okay, there is opcode plus there is operand here. There was only opcode here. Okay. And what I will be having in a 3 byte operation, so opcode plus 16-bit data. There will be a 16-bit data. Okay. And the first byte will be higher and second byte will be low order. So I can say that this is opcode. Then here first byte is coming here, which is giving me the opcode. Then there is a second byte, and then there is a third byte. So second byte is higher order or more significant, and third byte is a lower order data. Okay. For example, I can say let's say LDA 2050H. Okay. So now LDA, it basically means to write in H. So that is my opcode. 1 byte is here, right? And then in order to give 2050, I will be needing 2 bytes, because 20 and 50, this is total 16-bit data. So I will be needing 8 bytes for this 8 bits for this and 8 bits for this. So this is my second byte and this is my third byte. So total I am having a 3 byte instruction in this particular case. Okay, so there can be these 3 types of instructions in our microprocessor. Okay, now what I'm going to do is let's take an example of a program so that you will understand how exactly we are doing it. Now this understanding of these programs will help you understand the programs of NC and CNC also, because ultimately they are similar type of things only. Okay, so let's say we want to do load 2 numbers. We are having 2 different numbers in D and E register. Okay, so I want to load 2 numbers in my 2 registers D and E, and then show the result or put the result in C after adding them. Okay, so what is happening here basically, I want to have 2 numbers. I want to load 2 numbers in register D and register E, then I want to add them, and then I want to put them in C. Okay, so that is our sequence basically. What is happening here, and invariably first is I will be loading in my D. Okay, then I will be loading in my E, then I will be basically adding them together. Okay, and then I will be moving them to C. Now this is not the coding, this is not the program. I need to convert it into program. This is just the this is the way how it needs to work. Okay, so in order to say load into D, so we have already seen that it has to be MVI. Okay, so MVI where? In D. What? Let's say 2H. So there is a data that I have given. I need to put that data into D. So value 2 will be going to D. Okay. Then let's say I am saying load to E, so MVI E, and the value is 3H. Okay. So 3H will be going to E. So I have loaded these 2 registers here. Okay. Then the next operation will be, because I need to carry out the addition, and all the logical operations can happen with the help of accumulator only. Okay, so I need one of these values in accumulator. Right. So what I'm going to do, I'm going to move into my accumulator, let's say the value of D. So now this A will become equal to D. So what has happened here? This D is equal to 2, this made E is equal to 3, and now this will be making A is equal to D, which means A is equal to 2. Okay, so I'm having value of 2 in my accumulator. Now I can do the addition. Okay, so now add E. So what will that do? That A will be coming equal to A plus E, and that will be A older value 2 plus E value 3, and that will come now 5. Okay, so I am getting 5 after this operation. But what I do, what I want the final result in C. So what I will do here, simply move C from where? From A. Okay, so move the content of A to our C, then here finally I will be getting C is equal to 5. Okay, so that is how this operation can be done. Now that is all that I want, so there is a halt. That's it. Okay, so that is how we write the programs for a 8085 microprocessor, or for any other microprocessor for that matter, but just the commands and the sequence of these things only will change. Okay, now depending upon how exactly I am giving my instruction and how exactly I am giving the address of my operands. Okay, now so depending upon the operands and the addressing of those operands, I can define something called as addressing mode. Addressing modes. Okay, so let's discuss the addressing modes of 8085 microprocessor, which are mostly common with other microprocessors and microcontrollers also. Okay, so addressing modes in 8085 could be one, it is called as immediate addressing. Okay, so there is something known as immediate addressing. Now what do we mean by immediate addressing? Immediate addressing is when operand value is given in instruction itself. Okay, is given in instruction itself. When I have given the operand's value in the instruction itself. Okay, so what had I done here? When I said that to move 2H to my D, so this is my operand, right? So I have already given the value of operand into my instruction itself. I have already said that value 2 needs to be moved to the register here. Okay, so that is what we mean by immediate what do you call it, immediate addressing. There could be like add 32H to our accumulator, so that is also immediate addressing. Okay, that is an example. Now second type of addressing mode that we can use for our microprocessor is called as register addressing. Okay, that is called as register addressing. Now what is a register addressing? In register addressing, when operands are one of the internal register. Okay, when operands are one of internal registers. Internal register, if I am using as my operand, then it will be called as register mode or register addressing. Okay, so in this case, when I said that move the content of D to A, so I am giving the instruction in terms of a register, internal register. That is why it will be an example of register addressing. Okay, so that can also be done. Fine. Third is called as memory addressing. Okay, we have a memory addressing. In memory addressing, we can have okay, so what is that? Is one of the operands is in memory location. Then we will call it as a memory addressing. Now memory addressing can be of two types. One, it could be direct addressing. Okay, directly we are asking to the memory, or it could be indirect addressing. We are asking the memory but indirectly. Okay, so when we say direct addressing, means I will simply specify memory location in instruction. Okay, so that is what we mean by a direct addressing. So a 16-bit data of memory location will be specified into the instruction itself. Let's say, for example, LDA 2050H. So this is the location of the memory that needs to be checked out. Okay, indirect addressing is, as I told you initially, that HL pair of our registers can be used to describe the memory location. For memory location, we can use the HL pair also. Okay, so if I use HL pair, then I will be representing it with M. M will be its representation. So I can say simply here itself that move the memory location to our A. So that is also a type of memory addressing, but that is our indirect memory addressing. Okay, now there is last method, means the fifth method that we can have is called as input output addressing. Okay, so that is our fourth, but overall it's a fifth method. It is our input output addressing. Okay, so we have something called as input output addressing. So it's very simple, that 8-bit address of input or output port. Okay, directly the address of the port is specified in instruction. Okay, in instruction, then we will be calling it as a input output addressing. Okay, so depending upon from where we are collecting our operands, we can call it register addressing, immediate addressing, memory addressing, input output addressing, and so on. Okay, so we have already also seen one example of the program to make you understand how exactly it works. Similar type of programs are written in NC and CNC also. There is nothing, there is no big deal over here. Okay, now one thing that I talked initially about our RISC and CISC. So again, it is not a exhaustive list for RISC and CISC, and one thing especially, that it's not necessary that RISC is related with microprocessor and it is related with microcontroller and so on. Okay, there are just general conventions, not necessary ones. So this is known as our reduced instruction set computer. Okay, and this is known as our complex instruction set computer. Okay, so the full form is clear. So when I say reduced instruction set, means basically it only means that the number of instructions will be made shorter. Okay, we are not reducing the overall numbers, we are just making them shorter in size so that they can be executed a little faster. Okay, so it is a single cycle instruction, means in every cycle we will be executing a instruction. Whereas when I say complex instruction, so instruction can take several cycles. Okay, so one instruction can take several cycles. It can take more than one cycle to get completely executed. Okay, so that is like the main difference here. Usually we say that this is a software centric architecture, and this is a hardware centric one. Okay, and then we say that CISC is usually it is okay, in RISC we are having simple standardized instructions. Okay, so simple and standard instructions, fine. A small number of fixed length instructions, small and fixed length instructions. Okay, wherein here we will be having a complex type of system. So complex and variable length instruction and large number of instructions. Okay, so we will be basically having here complex and variable length instruction. So when I say that I am having all the instructions of same length or of similar type, then obviously it will be easier, a little easier and a little faster to execute those things. Okay, so these are like basic differences between our RISC and CISC. RISC we can, because it is a simple instruction, so we can directly convert our machine instruction to our execution. It can directly execute them. Okay, but in case of CISC it may not be possible sometimes to directly execute them. So therein it may happen that CISC will be there, that will be giving us the machine instruction. Now that machine instruction will be converted into a microcode. Okay, so it will be converted into a microcode first, and then that microcode will be generating different micro instructions. Okay, and then those micro instructions will be executed. Okay, so then there will be a final execution of the program or the instructions. Okay, so that is all that we have about our programming related to the microprocessors. In our next video we will wrap up the microprocessor and microcontrollers by looking at the remaining things, which are basically our peripherals and input output interfacing and all those things. Also some miscellaneous things related to microcontrollers and microprocessors. Okay, and we will be doing the questions also then only. Well, thank you for watching and best of luck.